probably not too many times that you would use RNN or LSTM. You would probably use a transformer. But you should always remember the Occam's razor. If a fully connected model can do it, don't use an RNN. If a RNN can do it, don't use an LSTM. And if an LSTM cannot do it, then go use a transformer, right? So this is in 112 lines of code using only NumPy. So if you look very closely, he has imported only NumPy. This is from Karpathy. This is a gist, and in this much lines of code, he is able to train this char level RNN. So the concept is really simple, and if you write 112 lines of code from scratch, you can train an RNN, right? He trained an RNN on William Shakespeare at the character level, and interestingly, that model was still able to kind of generate something. Initially, it generates garbage like this, then it starts to kind of form word-like things. It kind of has, you know, these quotations. Here, it kind of starts to form words like fall and that and the, but it doesn't form sequences. It doesn't form a complete sentence or a phrase. Here, it starts to form these phrases after more training. Here, you know, it kind of created something, but obviously it doesn't make too much sense. They also trained it on algebraic geometry. So algebraic geometry is again something interesting, and we can talk about it maybe in one of our classes. Algebraic geometry kind of studies the relationship between algebra and geometry. So they kind of trained it on LaTeX code for algebraic geometry books, and based on that, they can almost create LaTeX, you know, almost real looking output at the character level. They also did it for code, and with the generated code kind of looks like this. But this code was not useful. But you see, back in the day, back in 2014, 2015, people were already. So this is my course from 2015 at IIT Bombay. I taught the exact same slides, and by then we were already thinking about it. But this was not good enough to be used in any application. And it kind of learns that there has to be this preamble in the beginning. It learns that there has to be these include statements in the beginning, and then it does this, but obviously it will not compile because this is not correct code. Now he looked into kind of searchability of neurons in an RNN, which neuron is responsible for what. You can do it in an RNN, but as you go more complex like transformers, it becomes more difficult. So he found that there is a single cell that corresponds to quotation, right? That cell would go on and off, just like that neuron in the brain of the cat, right? Then there was a neuron for the line ending, so for sort of tracking the length of the line, and this was published as an ICLR paper. It's by Karpathy and Johnson and their PhD advisor Fei-Fei Li, the same professor who created the ImageNet dataset. He also found that there were neurons for the if statement cell, so it kind of kept track of when the bracket was opened so that it could then close the bracket at the right time. It also, but not everything was interpretable. There were, things that he could not explain, and this is maybe, the output of some neuron, which was not very directly evident because it's this complex, fully connected nature of that WXH and your WHH, right? So it's difficult to find of, to create that H, right? So it's difficult to kind of find meaning in each of these cells in the hidden state of the RNN. But it's an interesting exercise, and it kind of gives us some intuitive understanding of what goes on inside an RNN. So he did more on this, and I kind of will point you to that paper if you're interested. And now let's look at one concrete example where you want to find a caption for an image. For this image, you want to find a caption such as a straw hat, or a man's wearing a straw hat. And there are a bunch of papers in that time which was doing this. Today we have way more powerful models, but the genesis of all these powerful models is a decade ago, when we were already thinking about these models, right? So like we discussed briefly when we were talking about transfer learning, you take your image, you use your CNN to create these hidden states, right? So these encoding that this descriptor corresponding to this image, and then you input this you input this embedding into the RNN using this WHI, which is another fully connected mapping, right? So you will then have your WHI, which interacts with the output of your CNN vector. You will have the other two vectors as usual. You will do your tanh on top of all that, and that will give you the next hidden state. They have also tried to put in this into all the different steps, but it turns out that doing it only for the first one is more powerful. And this part is your CNN, this part is your RNN, right? This is your WHH, this is your WOH, this is your WHX. And what you do is you put this into, let's say, AlexNet. This is the AlexNet model. You get rid of the last layer, you take the second last layer, right? You take the output of your second last layer, you then put it into your model with this WIH, right? So you take your WIH, you call it V, and then you have your WIH into V, and then you get into your regular stuff. And this is what it was before, right, when we looked at the regular RNN. But when you want to do this, you can then put anything inside your RNN using this kind of a method. And then you do the same business, the sampling business, and you get a man is wearing a straw hat. And you also have this end token. When you're at the end, your model has these special tokens. In this case, it has this end token, and when it outputs end, it is time to stop sampling. It is time to kind of not do this business anymore, right? So you don't want to feed this end back into this. So that is what the end token signifies. And you get this end because that is how you have trained it. You have created your data where you have the different words followed by that end token, by that end word. So there are different image captioning data sets. This is really old, from 2014, so I'll skip it. And there are some so this is the vanilla RNN, and then you have so you can also write your vanilla RNN like this, because it's a tanh on the weight. You can stack these weights up, and you can create one weight matrix instead of these two weight matrices, and then you can simply have your previous hidden state, your current input at time step t, and your weight matrix. You do a tanh, and that is how you get your output. And you can then also stack them up, but more on that, so I would not worry about that, right? You can have like these different hidden layers. You can stack these up to get your final model. Here we were talking about just this one. And your LSTM is essentially this. So if you think about this, right, when you do your gradient flow, when you go from here to your gradient flow gets weak, and especially when you go through these time step, because you go through your W mapping, your gradients become very weak. And this is what Schmidhuber fixed in his LSTM. But again, I'm gonna very quickly skim through it. If you're interested, I would point you to Karpathy's 2016 lectures on YouTube, right? Most of these slides are from there, and he kind of goes into a lot more detail, but I'll skip through it because it's not very relevant in today's world. But we'll still kind of implement it quickly using PyTorch. We'll not do like manual backprop through it. I'm happy if you just do it using PyTorch. So he kind of changed this. So back propagation through your hidden by multiplying with this, w many times gives a lot, gives this problem in that vanishing gradient. And that is what you want to try and fix, and especially when you do it multiple times, it kind of gets really, really bad. And Bengio's student published an ICML paper in 2013 where he shows mathematically why this is a problem and how to try and fix it. And Bengio is famous for RNN because in 1994 he wrote this paper, learning long-term dependencies with gradient descent is difficult. And this is where he comes up. You remember I showed this paper when we were talking about weight initialization. So that is where he says, okay, if you initialize your weights, you can at least do a few time steps. You can at least do 6-7 time steps, and that is his chunk length. So he chunks his sequences into these 6-7. You can do that backward propagation in 6-7, and that is how he kind of trains the model. And whenever I say 6-7, I think of my kids, because whenever I say 6-7 these days, they kind of do that meme of that 6-7. So that is why I was smiling. And so whenever the largest singular value in this weight matrix is greater than 1, if you want to simplify it, let's say your weight is only this single number. Let's say it's either greater than 1, it's let's say 5, or it's less than 1, 0.1. Whenever it's greater than 5, you will get exploding gradients. Whenever it's less than 5, you will get vanishing gradients in a RNN. And you do things like gradient clipping and proper weight initialization, but it still is not the best. And this is where Schmidhuber in 1997 came up with this LSTM cell, right? So what does he do? He says that instead of having now this one hidden state that we had in our RNN, we will have these 4 hidden states, and he calls his hidden states these I, F, O and G. So the size will be 4H, and on 3 of them he does sigmoid, and on 1 of them he does tan H, and then he will multiply it with, so you will have this then you will kind of get this vector of size 4H, right? And then you will also, so you have this vector of size 4H, and there, all these hidden vectors also have names, right? So all these hidden vectors have different names, and then you will then concatenate it with, so this is your hidden vector, right? So this is your h of t minus 1. You will concatenate with your weight, and so this is how you get your these vectors, and from these vectors I'll show you how you get your final output, right? So these are your final so this is your these are your these vectors that you have, right? And from these vectors you can then do these operations. These are pointwise operations, multiplication, addition and tan H, to get your cell state and hidden state, right? And this cell state and these are what you take to the next level, right? So the cell state and hidden state is what you need to kind of do this backprop. I know I've completely rushed over this, probably you'll not remember, and you will definitely not be able to implement it, and I'm okay with that, right? Because it's not very important in my opinion. And with this you get this uninterrupted gradient flow, and this is why LSTMs were very powerful until 2017, right? So it reigned almost for 20 years, from 97 to 2017, and this is where transformers took over. And then there are some other RNN variants which are also interesting. For example, this GRU is one where it's which is sometimes used, at least previously was used, and your GRU looks like this. And then there is this paper in 2017 where they called LSTM a search space odyssey, where they try all these different combinations and they kind of get models which work equally, maybe slightly better than that LSTM. Because I'm sure you must be thinking, how did he come up with this approach, right? How did he know that he has to kind of do a sigmoid for the first 3 and the tan H for the next one? This is all a hyperparameter search, right? PhD students spent years of their life trying all these different combinations. Some of them work, and then we kind of take that for granted and kind of take it from there. Google, it's a similar story, right? They kind of tried so many different things, and that transformer worked, so now we've put all our eggs in that transformer bucket. So in summary, LSTM allows for RNNs allow for a lot of flexibility and architecture design, because we can now have one-to-one, one-to-many, many-to-one, all of that. Vanilla RNNs are simple but don't work very well. Common is to use LSTM or GRU. Their additive interactions improve gradient flow. Backward flow of gradients in RNN can explode or vanish based on the maximum singular value of your weight matrix. Greater than 1 is explode, less than 1 is vanish. Exploding gradient is controlled by gradient clipping, and vanishing gradient is controlled by these additive interactions using an LSTM. And better, simpler architectures are a hot topic of current research back in the day and even today, right? Even today, we're trying to find architectures which are better than the transformer. And more on that next week.